All right, then let's talk about section 3.4, and we're going to talk about the derivative as a rate of change. So previously in section 2.1, we introduced average and instantaneous rates of change. So now we're going to look at applications where the derivatives model the rates at which things change. So before we looked at changes with time, and now we're going to look at the cost, for example, the cost of producing steel and how that varies with the number of tons produced, or how the power output of a generator varies with temperature. So really we're looking at the way two things change, how one thing changes with respect to another thing. So anything we can be talking about, not just time in general. So we're going to talk about instantaneous rates of change. So if we interpret our difference quotient as the average rate of change of f from x to x plus h, then we can interpret its limit as h goes to 0 as the rate of change at which f is changing at a specific point x. So we've talked about this already. We've talked about this instantaneous rate of change. This is our definition of our derivative. So if we're talking about a specific time or a specific point x, we're looking at f prime of x sub 0. And that's going to be the limit as h approaches 0 of that difference quotient. So thus, instantaneous rates are limits of average rates. So this was our average rate of change, this one here. And if we're talking about instantaneous rate, we're just taking a limit of that function. So let's look at an example here. So a typical male's body surface area, S, in square meters is often modeled by the formula S is equal to 1 over 60 times the square root of W times H. So H is going to be the height. H is the height in centimeters. And W is going to be the weight in kilograms of the person. So let's find the rate of change of body surface area with respect to weight. So here we're finding the rate of change. So we know if we're talking about a rate of change, we're going to be finding what? Rate of change means we're going to find slope, which is, starts with a D. It's our derivative, right? So rate of change, way something changes, we're going to be looking at finding a derivative. And we're finding the derivative of the body surface area. So body surface area is, in this problem, it's S. Yeah. So that was too much there. So it's S. So we're going to be taking the derivative of S. And it says that we're finding it with respect to the weight. So we're finding the derivative of the body surface area, S, with respect to the weight. So we have to find the derivative. So we're finding S prime. That wasn't supposed to happen. So we're finding ds with respect to the weight. So dsd with respect to the weight, dw. So that means that w is going to be our variable. T isn't our variable, x isn't our variable, h isn't our variable, w is the variable. So h is going to be a constant, even though we have this formula here that has h as a variable. In the example that we're using, it's going to be a constant. So we're not taking a derivative with respect to h. It's going to be the derivative with respect to w. So the only variable that we're going to be considering is going to be w in this example. So that means that we need to separate that w and that h because we only want to think about the w as the variable. So S, I'll just rewrite S over here. S is going to be 1 over 60 times the square root of h, that's a constant, times the square root of w, that's going to be our variable. So when we take the derivative of the constant, 1 over 60 is a constant, square root of h is a constant. When you take the derivative, we're just going to leave those in there. So our derivative is going to be 1 over 60 times the square root of h. And then we need the derivative of the square root of w. So last time we did the derivative of the square root of x. And I said that was a common one that kind of comes up a lot. Do you guys remember what that derivative was? Derivative of square root of x, square root of w. How did that happen? Okay, so 1 over, yeah, 2 square root of w. All right, so that's our derivative. All right, so what else do we have to consider? So it tells us that we have a constant height h. So h is a constant, so we can plug that number in for h. So when h is equal to 180, our derivative, ds dw, and one way that we can show that we're going to evaluate that at 180 is just by drawing this horizontal line and writing 180 here, which means we're evaluating the derivative at 180. I should write, let's see what happens. Oh, I should write that h is 180 for this. Let's see if this will work here. Okay. So we're evaluating when h specifically is 180. So let's plug that in. Then we have the square root of 180. So, oh, this is s prime here, not just, oh no, that is s. That is s. This is the s prime that we want to look at here. So we have the square root of 180 divided by, and in our denominator we have 60 times 2. So I'll say divided by 120. And then we have the square root of w also in that denominator, times the square root of w down there. We have 60 times 2. The 60 times this 2 here. Where did I get the 2? From the derivative of the square root of w. So this was our function s. This was our function s, and we're taking the derivative of that function over here, s prime. So derivative of the square root of w is 1 over 2 times the square root of w. Okay? All right, let's simplify this then. So let's simplify square root of 180. So we're going to see if 180 is divisible by any perfect squares, if it's divisible by 4 or 9 or 36. 180. Oh, 9 and 20. But then, and 20 is also divisible by 4. So it's going to be divisible by 36. So 180 is the square root of 36 times 5. And when we simplify that, that's 6 root 5. So 6 root 5 divided by 120 times the square root of w. And then we can simplify 6 over 120. So we can cancel a 6 in the numerator with a 6 in the denominator. And we're left with 20 down here. And we end up with square root of 5 over 20 times the square root of w. All right, any question on that part? So that's the rate of change of the body surface area with respect to the weight for males of a constant height of 180 centimeters. So this is specifically 180 centimeters.
So wouldn't it be like square root of 5 or 20 for the, when you cannot plug it in M?
Plug in what?
Or it's not a
Okay. Does that make sense? To answer that question, because the first question says find the rate of change of the body surface area with respect to the weight. So we're finding the rate of change. So this is the rate of change. And this is for any given W. So if we're given a weight, then this is going to be the rate of change for any given weight W.
That'll be what it takes for it to change by a degree.
This is the rate of change of a surface area with respect to the weight. So it's more surface area. So the surface area changes of a person as their weight increases or decreases. So it doesn't have anything to do with, this doesn't have anything to do with the temperature or anything else. Yeah. Well, we were just doing this last time. So I just said, so the way that I got it is I said, what did we do last time? So if we have a function, f of x is equal to the square root of x, or x to the 1/2, and we take the derivative, it's 1/2 x to the minus 1/2, and that's the same thing as 1/2 x to the 1/2, which is 1/2 square root of x. So we did that last time a couple times. So I just said, what? This is where I took the derivative to, this is the derivative of the square root of w. This is the function, and this is the derivative of that function. All right, so after you plug in that 70 and you put it in your calculator, you get approximately 0.013363 meters squared per second. Did you get that same answer? All right, any question on that? All right, so not meters squared per second, that doesn't make sense. So it's meters squared per kilogram. And actually, it's not even meters, it's centimeters. Yeah, so centimeters squared per kilogram, not meters. All right, let's move on then to the next part and talk about motion along a line, displacement, velocity, speed, and acceleration. All right, so suppose that we have an object that's moving along a coordinate line, so an S-axis, and we can make that S-axis, we can make it horizontal or vertical. Its position S as a function of time is going to be S as a function of time t. So if we have this axis here, we're going to call this S. Let's erase this here. All right, so we're going to call that S. And that's going to be the position. It's going to be our position axis. So let's say that we have a point right here, which is going to be S, and it's going to be a function of time t. And then let's have another point where we're adding a little bit of time to this. Like we're starting at one time, and then we're adding a little bit of time and ending up at another point. So this is going to be S plus a little change in the position. And that's going to be, of course, a function of t plus a little change in the time t. All right, so this point is going to represent a position at time t. So this is going to be a position at time t. So right here is going to be our position at time t. And then this is going to be a position at time t plus delta t. So this is and at time t plus delta t. And then we can look at what happens when we move from one point to the other point. And that's going to be our change in our position. So we can call that our delta S. So we're starting at one position, then we're adding that delta S. Delta S is going to be the change in the position. So the displacement of the object over the time interval from t to delta t, so on your notes right here, you can see that delta t is going to be f of t plus delta t minus f of t. So if we take this position right here and we subtract this position right here, what we get is that change in our position, that delta S. All right, and then another definition that we have is our average velocity. So average velocity we're going to write as v sub AV, and that's going to be our displacement divided by our time. It's going to be our change of our s divided by our change of our time. So just like when we're finding slope, we have the change of y divided by the change of x. It's the exact same thing here. It's a change of our s divided by the change of t. All right. So that's our average velocity. And then to find the body's velocity at an exact instant t, we're going to take the limit of the average velocity over the interval from t to delta t as delta t goes to 0. So just like we were doing in the last section, we're finding the limit of that body's position, the limit of that displacement function. So our velocity, instantaneous velocity, is going to be the limit as delta t goes to 0 now, instead of h going to 0. But same concept. So what this is saying is that this is going to be, the velocity is going to be the derivative of the displacement function, the position function, with respect to the time. So velocity is ds dt. So velocity also tells the direction of motion. So if an object is moving forward, if you have a horizontal axis and it's moving forward, you're going to have a positive velocity. If it's moving backward, you're going to have a negative velocity. If you have a vertical axis, if the velocity is positive, it's moving up. If the velocity is negative, it's moving down. All right, speed is just going to be the absolute value of the velocity. So speed is just going to be a number. It doesn't have a direction. It's not going to be positive. It's always going to be positive. So it just tells the absolute value of the velocity. And the rate at which a body's velocity changes is acceleration. So just like if you're driving in a car, you have a velocity, you have a speed in a car, and you also have acceleration. So acceleration measures how quickly a body picks up or loses speed. So just like we know it to be, like if we're driving a car. And then a sudden change in acceleration, if you slam on the brakes of a car or if you hit an object with a car, that's called jerk. So velocity is going to be the derivative of the position function, and acceleration is the derivative of the velocity. So if a body's position is s, then the body's acceleration is going to be the derivative of the velocity or the second derivative of the position. And then jerk is the derivative of the acceleration. So it's the third derivative of that position function. So let's look at an example. So at time t, the position of a body moving along the s-axis is s is equal to t cubed minus 6t squared plus 9t meters. All right, so let me open this in another screen here where it'll be easier for me to write. So here's our position function. S is equal to t cubed minus 6t squared plus 9, and that's going to be in meters. So part A says to find the body's acceleration each time the velocity is 0. 9t, right? Thanks. So we have to find the body's acceleration each time the velocity is 0. So how are we going to find acceleration? So derivative, right? What do we have to find before we find the acceleration? Velocity. Let's find the velocity first, because this is saying each time the velocity is 0. So let's find the velocity. Velocity is the first derivative. We're taking the derivative of s, so we're finding ds with respect to the time. So ds dt. So that means we're going to find the function s. We're going to take its derivative, where t is going to be the variable. And that is equal to 3t squared minus 12t plus 9. All right, this problem says let's find the acceleration when the velocity is 0. So what do I do with that? So I took the derivative of t cubed, bring the 3 to the front, and then decrease the exponent by 1. So it tells us the velocity is 0. So what do I do with that information? Set the velocity equal to 0. So they say the velocity is equal to 0. So let's make v equal to 0. All right, so when v is 0, that's what they're telling us, 3t squared minus 12t plus 9 is equal to 0. So let's solve this equation for t, and let's find out the times when the velocity is 0. So if I'm solving this equation now, I'm not just randomly setting it equal to 0. They tell us that the velocity is 0. So I can factor a 3 out of that equation and get 3 times t squared minus 4t plus 3 is equal to 0. And then I can factor this quadratic, and this factors as 3 minus, or t minus 1 times t minus 3, and that's equal to 0. So the two solutions to that equation are going to be t is equal to 1 or t is equal to 3. So what's happening when the time is 1 and what's happening when the time is 3? The velocity is at 0. So that means that an object is moving and it stops moving and the velocity is 0. So when the object stops moving, it could continue in the same direction or it could change direction if the velocity is 0.
So it's equal to 3 and 1, not negative 1 and negative 3.
So using the zero product property, you set each of these factors equal to 0. So you would have like t minus 1 is equal to 0, and you solve that equation. And so it's positive 1 and it's positive 3. All right, so then we're being asked to find the acceleration when the velocity is 0. So how are we going to find the acceleration? So now find the acceleration. And acceleration is going to be what? So dv dt, it's the derivative of the velocity with respect to the time. So a, our acceleration, is dv dt, derivative of the velocity function with respect to the time. So what's dv dt? Yeah. Yep. So what is it? Yeah, that's it. So our acceleration is the derivative of the velocity, dv dt, so it's 6t minus 12. And they're saying to find the acceleration each time the velocity is 0. So this is our derivative, but this isn't the velocity each time the velocity is 0. How do we find the acceleration each time the velocity is 0? Yeah, so we're going to find the acceleration when t is 1, and then find the acceleration when t is 3. So I'm going to do that on another page here. So we had a is equal to dv dt, and that was equal to 6t minus 12. So when t is equal to 1, so after 1 second, the velocity is 0. Let's find out the acceleration. Velocity is 0, let's find the acceleration. A is equal to 6 times 1 minus 12, and a is going to be equal to negative 6. And then what are the units going to be for that, for acceleration?
Second squared.
Yeah, meters per second squared. So negative 6 meters per second squared. That's going to be the acceleration. And then let's do the same thing when the time is 3 seconds. A is going to be 6 times 3 minus 12. So 18 minus 12 is going to be positive 6 meters per second squared. So what this means is that it's going to be motionless. This object is going to be motionless when the velocity is 0. So at 1 second and 3 seconds, it's going to be motionless because we don't have any velocity. But there's going to be acceleration at that point. So it's motionless but accelerated. And the negative means that it's going to be accelerated to the left. So it's accelerated to the left when t is equal to 1. And accelerated to the right when t is equal to 3. All right, let's look at the second part, part B of this, and let's find the body's speed each time the acceleration is 0. So each time the acceleration is 0. So what do I do with that fact when the acceleration is 0? They tell us the acceleration is 0. What do I do with that?
So what would be equal to 0? B equals 0.
Not V, but A. Because they tell us that we have to find the speed when the acceleration is 0. So the acceleration is 0. Yeah, we're going to be on part B on the next page. So what we know is that our acceleration function is 6t minus 12. So when A is 0, we have 0 is equal to 6t minus 12. So when does that happen?
Add 12 to the side, divide 6, so at 2 seconds.
Yeah. So the acceleration is going to be 0 when the time is going to be 2 seconds. So we have to find the body's speed at 2 seconds. So we have to find the speed when t is equal to 2. So how do we get speed?
Plug in that for
A equals VT.
acceleration.
Huh? So what's our definition of speed from the previous page?
This
It's the absolute value of the velocity. So we're going to find the absolute value of the velocity. So absolute value of velocity when the time is 2. So we're going to take our velocity function and we're going to plug 2 into that velocity function from the previous page. So the velocity function, we had v is equal to 3t squared minus 12t plus 9. And so we're going to plug 2 into there for our time now. So we have absolute value of 3 times 2 squared minus 12 times 2 plus 9. So that's 12 times, or 3 times 4, which is 12. 12 minus 24 is negative 12 plus 9. That's going to be the absolute value of negative 3, and that's going to be equal to 3. And what are the units for this, for speed?
meters per second.
Whenever I need units, I'm going to call on you, Devin, because you're the units guy.
Yeah.
All right. And then C is asking us to find the total distance traveled by the body from t is equal to 0 to t is equal to 2 seconds. All right. So body is at rest. When the velocity is 0. Okay, so we know that, right? So when the velocity is 0, the body is going to be at rest. So that's when the direction can change. So the direction can't change unless the velocity is 0, right? You're not just going to be moving along and then it can change direction. When it changes direction, velocity has to be 0. So that's when the direction can change. All right, so when v is equal to 0, we already did this. So when v is equal to 0, what is t? So on the part A, we did this before. So we factored that velocity function. We set the velocity equal to 0, and then we factored it. And we said that the only time that the direction can possibly change would be when t is 1 or t is 3, right? So t is equal to 1 or t is equal to 3. That's the only time that the direction can change. It can't change direction any other time. So the direction can change. And they're telling us to find the total distance traveled by the body from 0 to 2 seconds. So if we're only considering 0 to 2 seconds, the only time that it can change in 0 to 2 seconds is at 1 second. Right? That's the only time that it can change direction. Only at t is equal to 1 second. Since we are going from t equals 0 to t equals 2. All right, so if we're looking at let's look at the time interval. So we don't know what's happening between 0 and 1 second. But at 1 second is the only time that it could possibly change direction. So we're going to see what's happening between 0 and 1 seconds. And then we're going to see what's happening between 1 and 2 seconds. And we want to find, this is asking us to find the total distance traveled. So we want to find the distance traveled between 1 second and the distance traveled between 0 seconds and the distance traveled at 1 second. And that will tell us the total distance traveled in that first second. So we're looking at, we want this to be the absolute value because we're just going to look at the total distance. So if we're looking at, if we're starting at this, if this is time, let's say this is time from 0 to 1 second, we want to find out what the position is at 0 seconds, what the position is at 1 second, and then subtract those two to get the total distance traveled. Does that make sense? So we want to find the position at 1 second, position at 0 seconds, and subtract those. So this is going to be S of 1 minus S of 0. So it's the position at 1 second minus the position at 0 seconds. And the same thing for this one, the second interval. We're going to take the position at 2 seconds and subtract the position at 1 second. And that will give us the distance traveled in that interval. So how do we get the position at 1 second? How do we get S of 1? How do we get S of 0? How do we get S of 2? So we're going to plug in 1 into which function? So if we're finding S of 1, this means we have to find the function called, if I'm finding f of 1, f is a name of a function, and I'm taking 1 and plugging into the function called f, right? But now I'm just calling the function s. So s of 1 means that I find the function called s, and I'm going to plug 1 into the function called s. So that's just the name of a function. So do we have a function called s? Previous page? That's our position function. So that's t cubed minus 6t squared plus 9t. So we're plugging 1 into that function. So what do you get when you do that? So you get 1 cubed minus 6 times 1 squared plus 9 times 1. So that's going to be 4. And what about when you plug in a 0? You get a 0. So the total distance traveled between 0 seconds and 1 second is going to be 4. That's what was given in the problem on the previous page, where it says example. That was given to you.
So S equals the distance.
Yeah. It's the distance traveled. So the distance traveled we get by finding the position at 0 seconds and the position at 1 second, and then subtracting them.
So, but why if S equals the distance, you said that the velocity is 0?
S is a position. S isn't a distance, it's position. Right.
So it can apply to distance and velocity. It's not just
S?
yeah,
S is a position function. It's a position at a certain time. So if we want to find the distance traveled, we're going to find the position at 0 seconds and the position at 1 second. So it starts here, it ends here. How far did it travel? We're going to find this position and then subtract that position to find the distance traveled. All right, so from 0 to 1, it travels 4. And then from 1 to 2, we got to find S of 2. So if we plug 2 into that function, we get what? Yeah, I think it's 2. So 2 minus S of 1, we already did S of 1. So S of 1 is 4, we already did that one. And so the distance traveled, the absolute value of 2 minus 4 is going to be 2. So the total distance traveled is going to be 4 plus 2, or it's going to be 6 meters. So what this one looks like if I were going to draw a picture of this displacement. So remember we had our axis, and this is our S-axis. So this is our position. So if the distance, if we start out at 0 and let's say that this is a 4 and this is 2. So the object in the first second is traveling 4 units or 4 meters. So in the first seconds, it's traveling 4. After the first second, that's when it can possibly change direction. So it's going to change direction, and then it's going to head back this way. And then it travels 2 more units in the next second from 1 second to 0 seconds. So the total distance traveled is going to be that 4 plus that 2. So this is the distance displacement chart here. All right, question on that?
What did he go back to?
Because that's when it can change direction. Because that's the 1 second. We said that that's when it can change direction. And then when we were doing when we did part A, when we found the velocity, we said at t is equal to 1, it's traveling in, the acceleration is negative. So we know that it's changing directions at 1 second.
Oh, because of the 6 centimeters?
Yeah.
So that's how we know.
And that's the only time that it can change is when that velocity is 0. So it's 0 at 1 second. All right, anything else? All right, let's look at the next example then on your notes. All right, the number of gallons of water in a tank t minutes after the tank has started to drain is Q of t is equal to 200 times 30 minus t squared. How fast is the water running out at the end of 10 minutes? And then what is the average rate at which the water flows out during the first 10 minutes? So let's first think about that first question. How fast is the water running out at the end of 10 minutes? So Q is going to be the number of gallons of water in a tank after the tank has started to drain. So Q is going to be the number of gallons of water in the tank, and then T is going to be our time. So I'm going to open up this page and write this function here. So what we know is that Q of T is 200 times 30 minus T squared. So if we're finding out how fast the water is running out, we're finding a rate of change of the water with respect to the time. So what are we going to find? What do we have to find? What do we have to do? What are we going to do with this function? So it's asking us to find how fast the water is running. It's not asking us to find the amount of water, because this is the amount of water. If you plug something into this function, you're going to get the amount of water. But we want to find out how fast. That means we want to find out a change, a rate of change. How do we find rates of change? How do we find the rate at which something is changing? Find the derivative, right? The derivative is going to give us a rate of change of a function. So we're going to take the derivative of this. How do we take the derivative of this amount of water? So we can FOIL first, right? Because we could use a product rule, but we actually have three things. We have 200 times 30 minus t times 30 minus t. So even a product rule is going to be a little tricky. So let's just FOIL that. So this is equal to 200 times, and if I FOIL 30 minus t, I get 900 minus 60 plus t squared. And then when I distribute that 900 inside that function, q of t is going to be equal to 180,000 minus 12,000 t squared, or just 12,000. This should be a 60 t in the middle here. So this is 12,000 t plus 200 t squared. All right, then let's take the derivative of that. So q prime of t, that's the same thing as dq dt. You don't have to write both of those things, just want to show you two different notations. So what is the derivative of that function? With respect to t. So 400t minus 12,000. Or you could put negative 12,000 plus 400t. All right, so that's our derivative. That's going to give us a rate of change of that function. So it's going to tell us how fast, what is the rate of change at which the water is flowing out of that tank. So the first question is, how fast is the water running at the end of 10 minutes? How do we find that? How do we find out how fast it's running at the end of 10 minutes? Plug in t. This is going to give us how fast it's running at the end of 10 minutes is what we get when we plug t into that function. So when t is 10, q prime is equal to 400 times 10 minus 12,000. And that's going to be 4,000 minus 12,000, and that's going to be negative 8,000. Units? Gallons? Gallons per minute. And the negative represents what? The tank is emptying. It's the loss of the water. So this tank is emptying. That's why it's negative. Emptying at 8,000 gallons every minute. 8,000 gallons every minute. So 1 minute, 8,000 gallons. And then the second part asks us to find the average rate at which the water flows out during the first 10 minutes. So average rate, so when we find an average rate, we're thinking about a concept similar to a slope where we're finding our change of y over our change of x. So the way that we can find that is a change of our q values divided by the change of our t values. So we can do delta q over delta t, and that's going to be the rate q at 10 minutes minus the rate q at 0 minutes divided by that time 10 minus 0. And that's going to give us our average rate of change. So we're going to take the 10 and plug it into q, into the original q function. That's going to give us the amount of water in that tank. at 10 minutes. So plug 10 in there. 30 minus 10 is 20. 20 squared is 4,000 times 200. It's going to be 80,000. And when you plug 0 into that function, 30 squared times 200, that's 180,000. Divide that by 10. And that's going to be equal to negative 10,000. And that units are, again, going to be gallons per minute. So that's going to be the average rate. So for any time t, the rate is going to be different. So here we specifically did it for 10 minutes, but if you're talking about the rate at 1 minute, it's going to be different than the rate at 20 minutes. So on average, it's going to be negative 10,000 gallons per minute.